The concept of forensic intelligence remains fuzzy, and consequently has led to difficulties in implementing methods in an operational environment. A clearer definition and conceptual advances show already important results, but this need to be further delineated. Forensic intelligence is still today often associated with the use of identification databases, such as DN, AFIS, shoe marks, ballistic, fingerprints, etc. And much of the debate has focused on those systems and mechanisms to introduce technology for extending similar tools to other types of traces. A definition of forensic intelligence based on computerized system can be interpreted as domain through its tools. This is undesirable. It is preferable to relate it with definitions coming from general theories of intelligence. We favor one that is completely abstracted from the under-printing technology. Forensic intelligence is the accurate, timely, and useful products of logically processing. Analysis of forensic case data, information for investigation and/or intelligence purpose. This definition points to how the collection, collation, interpretation, and dissemination of information of forensic case data can support investigation and broader intelligence programs. This non-traditional perspective potentially implies to revisit each step of the process, from what type of data has to be collected and how to organize them, to inferences drawn, organizations and communication channels to be designed. As a starting point, it has been chosen to concentrate on the study of logical interferences in order to show the variety of situations where the interpretation of forensic case data can combine with reasoning processes drawn in the course of the investigation in the generation of intelligence products. At this level, a general framework will better show the nature of contribution that forensic science should provide to the intelligence processes and help to derive particular operational implementations in functions of specific contexts and organizational structures. It is assumed that from information to intelligence, or in the course of an investigation, a reasoning process is carried out, which can be broken down into basic inference steps. These inferences can take a great variety of different levels of detail and require the use of broad variety of specialized knowledge, a scientific attitude, and potentially the integration of computerized tools. In the first phase of this study, it is proposed to identify and classify elementary reasoning steps that are used, routinely or occasionally, already in an intelligence perspective. These building blocks of our model will be called primitive forensic inferences. The first elementary form aims at recognizing a known person, even if he tries to hide his true identity. This inference was implemented as a structured and systematic process at the end of the 19th century through the Bertillon age and its main component, the anthropometrical system. It can be expressed in the following way. Compare the measurements taken from one person with a collection of measurements taken from previously condemned criminals. If a similar /close/ analog record is found, infer that both measurements come from same person. The same mechanism is obviously adaptable to use with other types of data, like fingerprints or DNA. It is routinely used when characteristics of a suspicious object are compared with a collection of descriptions of stolen objects. Of course, for each type of data, the processing constraints can be very different. The analogy must be specifically treated. How to implement concepts such as similar, close, and analog. The global efficiency can vary, as well as the content of the reference collection of persons/objects. If a similar /close/ analog record is found, infer that both records come from the same person/object. Of importance is the structure of the inference. It is not the topic here to define if the comparison process is computerized or how it is preformed. Primitive inference 2, the source. Historically, the use of fingerprints enriched the set of inferences by adding the possibility to connect traces with their source, and conversely, a source to traces associated with an investigation. A, source 2, previously unknown, race. Compare a print taken from a person with a collection of traces collected from crime scenes. If a similar /close/ analog record is found, then infer that the print and the trace are from a common source. This pattern can be generalized to integrate, for instance, DNA, ear prints, speech, CCTV images, and also physical objects such as shoes and guns. It can be formulated in the following way. Compare a print taken from a person/physical object with a collection of traces collected from crime scenes. If a similar /closest/ analog record is found, then infer that the print and the trace are of common source. B. Trace to previously unknown source. Compare a trace collected from crime scene with a collection of relevant inferences taken from the persons. If a similar /close/ analog record is found, then infer that the trace and the print are from a common source. This pattern can be generalized and expressed in the following way. Compare a trace collected from a crime scene with a collection of relevant reference prints taken from persons or objects. If a similar /close/ analog record is found, then infer that the prints are from a common source. Primitive inference 3, the link. Often regarded as side effects that are not really anticipated, DNA database provide a large quantities of links. Compare a trace collected from a crime scene with a collection of previously collected traces. If a similar /close/ analog record is found, then infer that the traces are from a common source. This formulation obviously applies to a wide variety of traces transferred from physical objects or persons and represents the basic inference in the detection of a linked series of crime. Primitive inference 4, the profile of the source. The objective here is to infer some useful characteristics of the source from an intelligence perspective, such as the color of the car, the height of a person, the shape of a vehicle, etc. From a trace, extract useful characteristics, descriptor of the source. It is not intended here to debate which characteristics are best to extract or how they are to be extracted. Primitive inference 5, the type of the source, classification. In order to perform this inference, the required knowledge consists of a collection of possible classes of sources. The inference can then be seen as a classification process. Compare a trace to a collection of descriptions of a reference collection of possible types of sources. Infer the types of possible sources. It is not discussed here which class, characteristic of the trace has to be extracted and compared. Usually, the type of source can be systematically inferred from collections of data, such as for guns, makes and models of cars, types of shoes, and so on. However, it has been shown that it is difficult to maintain an up-to-date knowledge of these different types of physical objects. Primitive inference 6, a list of possible sources. Often it is not possible to obtain unambiguous, highly definitive information from a trace. For example, the uses of putative, mixed or partial DNA profile information means that the comparison of such a sample to DNA database can result in not one single match, but in a list of possible sources. This inference can be generalized as follows. Compare a trace collected from crime scene with a collection of relevant reference prints taken from a physical object/person. Infer a list of possible sources. Primitive inference 7, a list of possible relatives. Similarly, some uses of DNA, particularly non-autosomal markers such as those of mtDNA in X and Y chromosomes, have the potentials to infer a list of possible relatives to the source. Compare a trace with a reference collection of prints taken from persons. Infer a list of possible relatives. Synthesis. Primitive inferences 1 to 7 form a basic framework for forensic intelligence, mainly based on analogical reasoning, which collates a great part of existing approaches and databases. This inventory does not pretend to be complete, as various items of information, such as those from forensic computing and intelligence provided by the analysis of mobile phone, have not been mentioned. It does not include consideration on inferences related to crime reconstruction and how his process should be modeled. These could include a sequence of shoe marks, the trajectory of a bullet, the relative positions of evidence at the scene, etc. It needs thus to be expanded. A wide range of the activities of forensic science laboratories can already be thought of as part of this framework, but unfortunately each trace is generally considered separately, and knowledge of the criminal context is seen as undesirable as it can potentially endanger the objectivity of the scientific process by introducing a so-called context effect. This relative autonomous component is generally seen as weakly coupled with other parts of the criminal justice system, as it seems to necessitate few or even to avoid entirely interactions with other partners. This misleading model is still often conveyed by major forensic scientists and their organizations that consider themselves as only provider of evidence for the court, largely disconnected from other parts of the criminal justice system. There is evidence that this attitude causes a net loss of information and ambivalence in the role played by each participant in the overall resolution of problems.